Okay, so from now on, we are gonna look at some of the applications of what we have been doing in this course. And today, this is lecture 22, and we will study applications to linear differential equations. So it turns out that the theory of linear algebra is extremely important to solving not only linear algebraic equation but also linear differential equations. So what is a differential equation? So I suppose you haven't studied differential equations, but you have certainly studied what are derivatives. So let's have an idea what's a differential equation. So a differential equation is just an equation which involves derivatives of functions in its expression. So for example, if you have a function y is a function of x, and you write some relation between y and its derivatives and x. So for example, if I write the second derivative of y with respect to x times x squared plus y times first derivative of x plus the derivative of x squared minus xy is equal to 3y squared. So it's just a relation involving your variable, free variable x, your function, which is a function of this variable, and the derivative of the function with respect to your variable. Some relation between them. So this is a differential equation. This is, I'm not going to go much into the classification of these equations because you can imagine that that requires full 2-3 courses. But we're going to study some very easy form of these equations. So what is the form we're going to study? So we will restrict to, if we restrict to the first derivative, so I'll just consider dy by dx and consider equations which are linear and homogeneous. So what would this mean? This would mean that I have the first derivative plus the function itself and some linear combination of them put equal to 0. So you can notice that there is no x appearing in the equation, only the function appears, and only the first power of function and the first power of the first derivative of the function. I use only these two things and I make a linear combination of them. And I don't even have a constant on the other side because I'm just considering extremely simple equations. These are not only all linear equations, it's linear and homogeneous. I don't have a constant on the other side, just a 0. So I'll try to solve these equations. You can solve a bit more complicated equations using the methods of linear algebra, but I will only concentrate on these kinds of equations. I'll complicate it a little bit though. So first of all, this thing, you can obviously write it this way. And this I can rename, let's call it A. So my equation is actually of this form. I make it a little bit complicated and consider a system of such equations. What does that mean? That means I have, first of all, let's give it a symbol. Let's consider, so system of linear homogeneous first order. By order, we mean how many derivative, order of differentiation. So just first derivative appears. System of linear homogeneous first order differential equations. And I'm going to consider, so what do I mean by a system? I have many functions. This is my function, and it's a function of, let's say, the variable t, because I'll be giving many examples where I consider this variable some function which is changing with time. So this looks nice to consider your variable. I'm only considering one variable, not more than one variable, but many functions of this variable. So you have this variable, and y1 is a function of t, but you have many such functions. And then you are writing then I define this just as a shorthand, dy by dt, I write it as y1 of t dash. So my system is a11 y1 plus dy2 by dt. It's also linearly related to all these functions with some constants. So on this I can call y1 dash and this y2 dash until you have yn dash. So these are some very restricted class of equations which I am considering. Even among the linear equations, I'm just having one derivative of one variable which is linearly related to all the other functions. So something like this. Now this I can write, I can arrange it into a column, let's call it y of t, which has all these functions arranged. Then y derivative of t is the column which arranges all the derivatives of these functions. Then this above linear system of differential equations, it can be written as y derivative of t. I'll many times drop this dependence on t, just not write it, where A is just this matrix. Matrix of these coefficients, right? I just multiply this matrix with this column y, I'll get these right-hand sides of these blue equations. And on the left-hand side, I have all these derivatives. So it's just writing those n equations in the matrix form. So I'm given these equations and they're defined through this matrix by giving these coefficients. And I want to find the solutions to these equations. How would you find the solutions? That's the problem. Find solutions for this system. What do I mean by find solution? Give the functional form for y of t. What is that function of t, or not one function? What are all these functions? y1, y2, y3 up to yn of t, which satisfy those equations. What would be those functions? That's the general problem. Find all those functions which satisfy this equation. So how do we do it? Well, we can start with the simplest one of them. So suppose you have just one function. Simplest case, that means you have dy by dt is equal to ay of t. How do I find it? I can just guess in this case. I can just check that solution is y of t is some constant, which I'm gonna write as x times a of t. X is a constant and the function is ea of t, exponential of t, with a appearing over here. Now this x could be anything. This could be any number and this equation will still be satisfied because you can very easily check. If I do dy of dt of this function, let me for now write this constant. I just don't want to create confusion as some constant. So if I take a derivative this is equal to a comes outside, and the derivative of exponential brings down an a, small a, and the exponential is reproduced back. So this thing is just y. So is equal to ay. So I have reproduced my equation. So that means y is equal to AEAT is indeed a solution. It's in fact the most general solution. Is the most general solution. And for each value of capital A, you have one solution. You have one solution. You haven't changed the equation, but you can still change this capital A and your function still satisfies this equation. So sometimes you can fix this value of capital A. This freedom allows you to solve initial value problems. That means if you are given the value of y at some initial time t, then this a will be fixed. For example, if you are told that at t is equal to 0, usually you're given the value of this thing, this quantity y, at the start of the time t is equal to 0 in the beginning. So if, for example, if you're told that at t is equal to 0, y is equal to 2, so then in your solution, y is equal to a e a t, you put, gives you 2 is equal to a e a at 0. At t is equal to 0, you just put it over there. So this is 1, exponential of 0 is 1. So that means a is now fixed to value 2. So with these initial conditions, your function would be would be 2EAT. So for example, if you have some infectious disease and y is suppose y of t is the number of infected persons at a given time. I'm just trying to make up some extremely simple model of spread of infection. It turns out it's actually way too simple, but as just a model, as just an example for our mathematical setup, it's fine. I can do whatever I want as long as I don't expect it to be very accurate with the real world. But suppose y of t is the number of infectious persons at a given time in a population, then the rate of change of y, that means how the infection is increasing, is going to be proportional to be proportional to how many people are already infected. So for example, each infected person can infect, has a certain probability of infecting other people. So obviously if you have 10 people and each person, for example, has a probability of infecting another person at the rate of, let's say, at the rate of 20% probability of infecting one person a day, then each one of them can infect other people. Then the rate of change in infection will be proportional to how many infected people you already have. And you will have a constant telling you what is that rate of, what is the probability of that infection to increase. So suppose each person has a 20% chance of infecting one other in a unit time, and this unit time could be anything, for example, 1 day. So then this is telling you rate of change of infected people per day. So as we have seen, this equation, its solution is this. And suppose at the day 0, you're starting from some day and calling it the date 0, you have, let's say, 100 infected person, you start from 100. That would imply A is equal to 100. So then your solution becomes y is equal to 100 t. Now, if I put t is equal to 10, what happens on the 10th day? On the first day, you have only 100 people infected. On the 10th day, you will have e to the 2. So 100 into so around about 800 people infected. But if you consider what happens on the day 20, or let's say on the day 40, so then it increases very, very, very quickly because it's 100 into 2.67 to the power 8. And similarly, if I increase the number of day again, it increases as a power. So this is called the exponential growth. Because the rate of change is proportional to the quantity itself, the resultant answer is an exponential growth. On the other hand, if you had something proportional to a negative number, let's say like this solution would be, so this quantity, you start with something, decreases very quickly, goes to zero very, very fast. So that's the exponential drop. And this is exponential growth. If you are considering, for example, compound interest, you have some wealth, y of t, and you have invested it somewhere where in a unit time, that could be 1 year, you get 10% profit. So that means the rate of change of your wealth is equal to how much you have, how much more wealth you get per unit time. It depends on how much you have, how much you start with, and you get 0.1 times of that. That's the rate of increase. So the solution is this is your starting wealth. So it's gonna increase slowly, but it's an exponential growth. With time, it's just really gonna explode. So that's why compound interest over time increases the wealth by a lot. You can put some numbers and experiment. Like if you have like 10% increase, you get it doubled in the first 7 years, but in the next 7 years, that double is doubled. In the next 7 year, even that is doubled. So you get doubled in 7 years, but in 21 years, you have 8 times the wealth. And then in 28 years, you have uh, 16 times your starting wealth. And then it just keeps going. Now, this was the solution if you had one variable. So in a similar situation, when you have many variables, and I have, again, let me just quickly write, you have more than one variables, and you have equations of this kind. Which I was writing as y dash is equal to a y, where these y's are the arrangements of these functions in the column. Then I can try a solution. Let's try to build a solution. And from previous example, I try this thing. Let's, these y's, because these are vectors, let me put an arrow on them. I consider something like this, a constant x1 times an exponential, another constant, and I am using the same exponential. So actually, I can bring out this exponential, So I have this kind of solution. I don't know yet that if it's going to be a solution or not. I'm just trying to guess the form by comparing with the case when I had just one variable, one function. So it's saying that each y1 of t is of this form. You choose a constant xi and then just you pick an exponential. But this exponential, in the case of one variable, you remember that this constant appearing in the exponential was not arbitrary. It was the exponential which appeared in your differential. It was the number which appeared in your differential equation. So here, this cannot be an arbitrary number. It has to be related to, must be related to your equation. And our equations, they are defined by this matrix A. So it must be something related to A. So let's see that what it could be, and let's see if it's a solution or not. So for this to be a solution, if I take a derivative of it, so if I consider the derivatives, this column of derivatives, this would be these, because I'm assuming this form of function. So when I take a derivative of each of these, I just bring down a lambda. So I can write this lambda outside, and I have lambda t. But this e lambda t times the x, that's just y. So that means y dash of t would be lambda y. And now I want to see if when it will be a solution. So if I suppose if this x is an eigenvector of A, then see what happens. So if it's an eigenvector of A with eigenvalue lambda, that means x is just the column of all the constants, x1, x2, x3, xn, which I had chosen. So if it were an eigenvector of A with eigenvalue lambda, then see what will happen. Then I will have y dot is lambda y from here. That means lambda e lambda t, because y is e lambda t x, but x times lambda, this is equal to ax from here. So that means I will have a times e lambda t x, and this thing is y, ay, and this was my starting equation. That means y is a solution. So that means y is a solution. Y is equal to x e lambda t is a solution if x is an eigenvector of A and lambda is the corresponding eigenvalue. So that means, how do you find the solution? So this is the recipe of finding solutions. Take this A, which defines this linear system of equations. Take A and find its eigenvectors and eigenvalues. So suppose you have eigenvector x1, x2 up to xn, and eigenvalues with eigenvalues lambda 1, lambda 2, lambda n. In our above analysis, it didn't say which eigenvector. Any eigenvector would do. Then for each eigenvector, we have a solution. So you will have y1 e lambda 1 t is a solution, y2, and so on. They are all solutions. You can check any one of them. If I pick this, y2, I take a derivative, x2 is constant, I will have lambda 2, e lambda 2, t. This combined gives me ax2. So this is written over there, a lambda 2. So all of them are solutions. Not only that, you can check a linear combination of two solutions is also a solution. So for example, if I take alpha times x1 e lambda 1 t plus beta times x2 e lambda 2 t. So let's call this just y1, where y1 is a solution, beta y2. Now if I call this a new function, y, and compute y dash, it would be alpha y1 dash, these are all vectors, plus beta y2 dash. Since y1 dash and y2 dash are solution, y1 dash, that means must be equal to a times y1, and y2 dash is a times y2, because y1 and y2 are solutions. So they satisfy my system of linear differential equations, my given differential, the system of given system of differential equations. So if I place this over here, I get alpha a y1 plus beta a y2. So this is equal to, so it's my ay, this thing. That means y is a solution. So this means because I have n eigenvectors available for any matrix, I will have, the general solution would be y is equal to a1 for each eigenvector. I collect each eigenvector and each eigenvalue. Let me write it as some linear combination C1, C2, where Ci are any arbitrary constants. Again, if you are given some initial values for these functions at t is equal to 0, and if you're given n values for n of them, you're given the initial value, then you can find C1, C2 up to Cn. So let's take an example. So suppose your system is this one. You're given two functions and their derivative is related linearly like this. So you have y1 dash, y2 dash is equal to 3, 4, 3, 2, y1, y2. This is your A, and it has eigenvalues 6 and -1, and the one eigenvector corresponding to this is 4, 3. I'm not just computing it, just writing it. 1 minus 1. Then your general solution would be equal to C1 E6 T 4, 3 plus C2 E minus T 1 minus 1. So suppose you are given that at t is equal to 0, y1 is equal to 6 and y2 is equal to let's say 1, then what would that mean? That means y1 is 6, y2 is 1, and this is equal to c1. I'm computing it at 0 time. So I get 4c1 because this is 1 and this is also 1 plus c2 and 3c1 minus c2. So this gives me c1 is 1 and c2 is 2. That will solve it, as you can easily see. So my solution with these initial conditions is E6t x1, you can write it like this way, x2. And you can notice one thing over here. The solution, it's gonna have this part at late times, this part keeps increasing and this keeps decreasing. So this one becomes extremely important at late times and this becomes increasingly less important. So this part is dying down while this part is increasing exponentially, very fast. And this part is dying down very fast. And what's special about this part and this part? The part which is dying down because of this negative number. It's a decreasing exponential. And why did this negative number come in? Because you had a negative eigenvalue. So if you have a negative eigenvalue, that solution, that part of solution just dies down with time, while this increases exponentially because you had a positive eigenvalue. Then you can have a steady state if, so suppose if you have, well, let me just do an example and then this will come out. So another example. Let me try to make it a bit more interesting. So suppose you have y1 of t is 2y1 minus y2, and y2 of t, this derivative and this is derivative, is minus 2y1 plus y2. Then I have one and it is this matrix which is A. Now for this matrix, I want to find eigenvalues. You can notice, let's do some of the things which we proved last time. Put them to use. You notice that the determinant of A in this case is 0 because it's 2 minus 2. But determinant of A is the product of the two eigenvalues. And if it's 0, this implies at least one of them is 0. So 0 is an eigenvalue, you just know it. And I also know that the trace of A is the sum of the eigenvalues. So one of them is 0, then the other one must be equal to the trace of this, which is 3. So the other eigenvalue is 3. So I have just found the two eigenvalues, lambda 1 is equal to 0 and lambda 2 is equal to 3. Let's find out the eigenvectors. So eigenvalues are lambda 1 is equal to 0 and lambda 2 is equal to 3. Then the lambda 1 eigenvector is vector x1 with eigenvalue lambda 1 is equal to 0 is just this vector, which gives you, when you act with this matrix, so it's some unknown. I'm writing it as x1, x2, and it's x1. Over here is x1 vector. These are these x1, x2 numbers. Do not confuse this x1 number with this x1 vector. I just don't want to keep introducing new symbols. So what do I get from here? This gives me 2x1 minus x2 is equal to 0, and the lower equation gives me minus 2x1 plus x2 is equal to 0. So they are not different. The second one is just the first one multiplied with a minus 1. So all it requires is 2x1 is equal to x2. So one option is I choose x2 is equal to 1, x1 is equal to 1. If I put x1 is equal to 1, then x2 is equal to 2. So it's 1, 2. So 1, 2 is an eigenvector. And you can check. Two minus 2, 0, minus 2 plus 2, 0. It is an eigenvector with eigenvalue 0, because this is equal to 0 times 1, 2. And what's the other eigenvector? Eigenvector x2 with eigenvalue lambda 2 is equal to, what was the other eigenvalue? 3. 3 is 2 minus 1 minus 2, 1, some unknowns, and I will produce these unknowns with a multiplied, with the vector multiplied by 3. So I get 2x1 minus x2 is equal to 3x1 and minus 2x1 plus x2 is equal to 3x2. And this gives me minus x1 minus x2 is equal to 0, And when I bring this guy to the other side, it again gives me minus 2x1 minus 2x2 is equal to 0, which is just the first one multiplied by the 2. So this gives me x1 or x2 is equal to minus x1. So I can choose 1 minus 1. This would be the eigenvector. Remember, the eigenvectors are not unique. I can scale them by a number. But this is one choice. So then I get the solution is is C1 E0 of t, and the eigenvector was, first eigenvector was 1, 2, plus C2 E3t 2 minus 1. So this, if I have a 0 over here, so this just goes away. This is just 1. This is just a constant. Now suppose if I start in this, that y1 is 1 and y2 is 2. That would mean that I'm starting in this vector. So at the start, this C2 must be 0. But if it's 0 at the start, it's just a constant, it's just 0. That implies that the solution would be, and C1 would be 1, is just this. But this is just a constant. Nothing changes over here. This is a y of t is a constant and which never changes. On the other hand, if I started in if at t is equal to 0, y1 was 2 and y2 was minus 1, this vector, then this would imply that C1 is 0 and C2 is 1. So then y of t would be 2e3t and minus 1e3t. These increase with time. So the point is that each eigenvector which appears over here, you should think of it as one independent solution. And many a times they are mixed. You have to add both of them with certain ratios. But each one of them evolves with its own exponential factor separately. So in general, you have a solution through an eigenvector which evolves with this eigenvalue. If this value is positive, then this part, this solution, increases with time. If it's negative, it decreases with time, and because e to the minus lambda t goes to 0 at late times as t increases, so this dies down. But you can also have lambda 1 is equal to 0. You can have a 0 eigenvalue. Then all the time dependence drops. If you have this and lambda is 0, then this is just x1. Then you have a constant as a solution. So that part of solution will just stay there. That will not change with time. So this tells you something like some steady state in your solution. But then we have another problem. The other problem is that you may have complex eigenvalues. It's not necessary that the eigenvalues will be only plus, positive, negative, or zero. They can even be complex. So what happens in that case? That's the question. Well, let's consider. So suppose you have a complex eigenvalue lambda 1. Well, let's say you have one complex eigenvalue lambda. Then we proved it last time. If you have one complex eigenvalue, value lambda, so that ax is lambda x, then x would also be, can also be complex, but a is real. So if I take complex conjugation, just splits, and when I take a complex conjugate of a, it's real, so nothing happens to it, and I get this. So this is saying that the complex conjugate of the complex eigenvalue which you know of, you have found one complex eigenvalue lambda, then its complex conjugate lambda bar must also be an eigenvalue. With eigenvector x bar. You don't even have to find the corresponding eigenvector. That would be just be equal to taking the complex conjugate of the eigenvector corresponding to eigenvalue lambda, and that's just will be a new eigenvector. So complex eigenvalues always come in pairs. Always come in pairs. We had discussed it before. So that means if I am doing a 2 by 2 system, then if I have one complex eigenvalue lambda, the other one would be lambda bar. If I have a 3 by 3 system, if I have one complex eigenvalue, there will be another one lambda bar, and the third one has to be real. Let's call it lambda 3. Has to be real because it doesn't have uh, it cannot have its pair, because you have in a 3 by 3 system you have only 3 eigenvalues. In 4 by 4 you may have something like this, and the other two may be real, or if again you find another complex eigenvalue lambda 3, then the fourth one would be its complex conjugate. The point is that they always come in pair. So suppose if, let's for simplicity start with a 2 by 2 system. You are given again this system. System of linear differential equations. And you find a complex eigenvalue. Lambda. Let's write it as a plus iota b. Then you still have whatever we had done. That still is true, that you will have this as a solution. This is a solution. With this thing complex and this thing complex. This is one solution. Then you will also have this solution. This is also a solution. Now I know that since any linear combination of them is a solution, so I make this linear combination. So it's equal to half y1 plus y2 and call it lambda 1 tilde. So this is just half e a I'm explicitly writing this lambda as a plus iota b of t plus a iota e of t, and this x will have a real part plus iota and imaginary part, where real part of x is just, let's write it explicitly over here. If you have x, these guys this time are complex. So you will have real part of x1 plus iota, imaginary part of x1, real part of x2 plus iota, imaginary part of x2, and so on. Remember that real part of x1 is a real number, and imaginary part of x1 is also a real number. So if you have something like this is called the real part, this is called the imaginary part, and they are separated by an iota, but both of them themselves are real numbers. So this thing I'm writing as separating it out where real of x is just a column of these plus iota a column of these. So if I do this, then this guy, this becomes half e a plus iota b of t times real of x real of x1 plus iota imaginary of x1. Then I'm adding to it half the other eigenvalue, bt, and real of x1 is the complex conjugate. So if I collect these, this I take common, I will have real of x1 plus real of x1 and plus half EAT. Then this time I collect these guys with an iota. So this part coming with this and this part. So they cancel because there's a negative sign. So that doesn't appear. Now I have half E iota bt and plus half E minus iota bt. They are, I have real of x1. Real of x1, yeah. So this part will become cosine of bt, because if you recall, what is the expansion of cosine? I can write cosine of x as e of iota xt plus e of minus iota xt over 2. So we will arrange these and then you will have, what I'm trying to do is write the solution as a real solution. Right now, what I had was a complex solution. I'm trying to make the linear combination so that I get something real. So since we are running out of time, we will complete it next time.